Okay. All right. Hi, guys. Today we're talking about Zerocheck again, and we're talking about the second part of the three-part lecture series. Um, Specifically, in this part, we're just going to be talking about Sumcheck protocol, what it is, how it works, why it works. Um, Last time we talked about some mathematical preliminaries, which will be useful to understand in order to be able to fully understand this section. We talked about like why Zerocheck matters in the context of a snark. And we also talked about how we can reduce Zerocheck to a Sumcheck instance. So with all of that context, basically today you can black box that all away and you can just pretend like you were given some Sumcheck instance and now you want to prove it as a prover. So yes, we will be talking about the Sumcheck. We won't be talking about where it came from in the Binius snark and other types of proof systems. So yep, this is what we'll be focusing on today. The goal of today and the goal after you've reviewed this lecture is that you should be able to understand the Sumcheck protocol at a level where you don't need to look at the code or anything in order to be able to write down the algorithm for how Sumcheck works. You should have a good enough understanding of what Sumcheck is and what it's doing, such that you could literally just like write down the algorithm by yourself without having to look at it. And once you get to that level, it's going to be really nice because Sumcheck is at the heart of what this company does. It's even part of our polynomial commitment scheme. And being able to just have that level of familiarity and comfort with Sumcheck is really important if you want to be able to have interesting and in-depth technical discussions with Nikita, Ben, or Jim, or these types of people about how we can optimize the protocol's implementations even further. So this is really probably going to be the most important lecture that I give during my time here. Just explaining Sumcheck, what it is, how it works, and hopefully after this, watching this and maybe reviewing it a couple times, you'll feel very comfortable with this material. But as always, feel free to interrupt me during the lecture, ask any questions you want, and feel free to ping me after the fact whenever about whatever question or misunderstanding you might have. So, with that intro out of the way, let's dive right in. So, we discussed some mathematical preliminaries, and just to quickly recap what's most important, you should be familiar with what a multilinear extension of a function is. We have a function that has some Boolean hypercube input to field element output mappings, right? So this is just some arbitrary mappings of inputs to outputs. There is a multilinear polynomial, a unique one, in fact, on n variables, uh, such that this polynomial's inputs over the Boolean hypercube evaluate to the same thing that this function's inputs would evaluate to. Like these guys agree, f twiddle and f agree over the Boolean hypercube domain. The second thing you should be familiar with is what the individual degree and total degree of a polynomial is. And the final concept that you should feel comfortable with is that if we have two univariate polynomials, if I want to check whether they're equal or not, I can check whether their evaluations at a random point are the same or not. And that's actually a very good test to check whether these two univariate polynomials are equal. If they're the same polynomial, their evaluations at a random point will always be the same. If they're different polynomials, then their evaluations at a random point are unequal with extremely high probability. So this is called equality testing of univariate polynomials. These are the three things that if you're watching this recording and one of these three things is not clear to you, I would recommend going back to the previous lecture and recapping that. There's a little bit more math machinery that I need to introduce before we can dive into this topic today. And that's the concept of a multilinear composite. So if I have a multivariate polynomial f on n variables, it can be represented as a composition of multilinears. So let's look at an example to explain this. We have f of x0, x1, x2 is equal to this expression. So I can define a couple multilinears, and I can define a composition polynomial G. I define H1 like this, H2 like this, and G like this. Now I can see that F is actually equal to G applied to first evaluating H1, then evaluating H2, then applying G on those two multilinear evaluations. So F, or any multivariate polynomial, can be represented as a composition of multilinears. This is one way to represent it. There's reasons why we do this. Just a technical note, doesn't need to be talked about too much right now, is that the reason we do this is because, well, one, it like sort of mimics the structure that we care about from the snark, and two, we have multilinear polynomial commitment schemes. Not, we we technically don't have a way to commit to a multivariate without committing to its underlying multilinears and also revealing the composition function. So this is usually how we will represent a multivariate polynomial, as a multilinear composite. So in this example, G is a composition polynomial of total degree 3. H1 and H2 are multilinears. Here's a fact that's important. The maximum individual degree of a multilinear composite is at most the total degree of G. So rather than prove this, I'll just show you in this example why that's true. If we look at the individual degree of x0 and f, that is 2. The individual degree of x1 and f, that is the max of 2 and 3, that's 3. Max of 2 and 3, that's 3. Individual degree of x2 and f is 3. Okay, so the maximum individual degree of f is the maximum of 2, 3, and 3, which is 3. And the total degree of G is 3. So in this example, we see the maximum individual degree of f is bounded above by the total degree of G. And maybe you can look at this and convince yourself that this is true, right? If G is of total degree 3, right, everything in here is coming from like a multilinear, right? So it can only bump up each individual variable x x's degree by whatever the total degree of that monomial term is in G. It's okay if you can't fully prove that, but hopefully you have some intuition for the fact that this is true. That G's total degree is an upper bound on the maximum individual degree of this f. Cool. Now, how would we evaluate f at a point x? Well, it's defined like this, and we're given its representation like this. What you do is you evaluate each of the underlying multilinears at the point x, and then you take these evaluations of multilinears and you apply that as the input to G. And that gives you the evaluation of f of x, right? So there's two things that I've done in this section. I've defined what a multilinear composite is and what it is. And second, I've sort of indoctrinated you a little bit with the notation that I'll be using henceforth, right? Specifically, G will be the composition, HI is going to be the multilinears that are underneath F, F is going to be the multivariate, D is going to be the degree of G, the total degree of G, and C is going to be the number of underlying multilinear polynomials. Hopefully it should be clear from context as we continue, but I'll be keeping this notation consistent as we talk in the upcoming sections. So that's the math machinery that you need in order to be able to understand Sumcheck. So now we're going to ignore the context of the snark and of Zerocheck, and we're only going to focus on understanding Sumcheck protocol. The three questions: what is it, how it works, and why it works. So without further ado, overview of the unoptimized Sumcheck protocol. Sumcheck, let's define it. It's an interactive protocol where a prover convinces a verifier of a claim, and the claim relates to a multivariate polynomial f and a claimed field value s. And specifically, the claim is that if you sum up the evaluations of f over all the Boolean hypercube inputs, then you get this value s, the claimed value s. So this is what the prover wishes to claim to the verifier. Now, let's make an assumption that the verifier is able to query F at some point R. Maybe just for to make very clear, I'll say this is L, but that's not so important. So yeah, let's just say that the verifier is able to query F at some point. Now, the key is the verifier does not want to do 2 to the n queries of F and add up all the results themselves because this is inefficient. The whole point of a prover in these protocols is to make the verifier have to do sublinear work, very small amount of work. That's like goal of the prover. So we can say that the verifier doesn't want to do 2 to the n queries of F, but maybe the verifier is okay with doing 1 query of F, right? And note bene, a technical note is that the way that they will query F is through polynomial commitment schemes and opening proofs. We won't talk about that today, but that's another protocol that you may be familiar with. It's called eval check. Anyways, let's assume that the input polynomial to the Sumcheck is always going to be represented as a composition of multilinears, a multilinear composite. So something like this, where G is a C-variate composition function of total degree D, and HI is an n-variate multilinear polynomial. And we say that F is an n-variate polynomial of maximum individual degree at most D. Let's preview what's about to happen. What's about to happen is the prover and the verifier are going to interact for n rounds. And in every single round, we're going to reduce a Sumcheck claim to a simpler Sumcheck claim. And what do I mean by simpler Sumcheck claim? A Sumcheck claim is, for like a k-variate polynomial, a claim about summing over k dimensions of the hypercube. So a claim over 2 to the k terms that you have to sum up over. A simpler Sumcheck claim is on one fewer variable and one fewer dimension. It's a claim about a k-1 variate polynomial and over k-1 dimensions of the Boolean hypercube. And that has 2 to the k-1 terms that you need to sum over in order to check whether the claim is true. So before round 0, we have a claim about a sum on the n-dimensional hypercube, something that looks like this, right? The sum over all n-length bit strings of f0 applied to that bit string is equal to S0, some claimed value. Then after round 0 and before round 1, we've reduced this thing through some protocol to a claim about a sum on the n-1 dimensional hypercube, right? F1 is now a multivariate polynomial on n-1 variables. We're summing over n-1 length bit strings and, applying F1 to those bit strings and checking whether that sum of 2 to the n-1 terms is equal to S1. Kth round, the claim is about a sum on the n-k dimensional hypercube. For example, something that looks like this, where fk is a multivariate polynomial on n-k variables. And this sum over 2 to the n-k terms is equal to sk. Finally, in the last round, before round n-1, the last round, the claim is about a sum on the one-dimensional hypercube. So we have a univariate polynomial, multivariate on one variable, and we take its sum over the one-dimensional hypercube, Vn01, and we ask whether that's equal to this value Sn-1. And finally, we have a claim about a sum on the zero-dimensional hypercube, which basically is just like this multivariate polynomial on 0 variables. There's only like one way you can pass in no input. Is that equal to Sn? And Fn, like you might be like, okay, what is this? It looks something like this, like F, but with all of its n variables specialized to specific values R prime I. So what's going on is at the end of n rounds of Sumcheck, we have an eval check, right? Which is asking like if Fn applied to nothing, or in other words, this is equal to Sn. And the desirable property is that like the we're doing some protocol to take us from like round k to round k plus 1. And it should be the case that like if this claim is true, then with high probability this claim is true. And if this claim is true, with high probability this claim is true too. And so like we do these sequence of reductions, and like a reduction is useful if the simpler claim is a good proxy for telling us whether this claim is true. The truth value of this claim is very, very, very closely linked to the truth value of this original claim. Now, in our code, we had to make some choices about interfaces. As you can imagine, round 1 versus round 7 of Sumcheck is going to look very similar. So the way that we've sort of made our Sumcheck protocol look programmatically is that the interface is you take in some Sumcheck claim and it gets reduced to an eval check claim. Something like this. So it does like n rounds, and eventually you get out an eval check claim. As like a computer scientist that loves invariance, I would say that the better way to think about it when you're trying to understand it is to think about Sumcheck as not a protocol that takes a Sumcheck claim and turns it into an eval check claim, but to think about it as a one round, and it turns a Sumcheck claim on like k variables into a Sumcheck claim on k minus 1 variables. And it just so happens that a Sumcheck claim on 0 variables is the same thing as eval check. So you can slice it up however you want. You can call this whole thing a protocol that reduces Sumcheck to eval check, or you can call like this thing a protocol, each of these guys a protocol that reduces a Sumcheck claim on k variables to a Sumcheck claim on k minus 1 variables. I claim that it makes more sense to do the latter, to think about it. It's just round by round. What's its job? To reduce from k variables to k minus 1 variables. And with the understanding that a zero-dimensional hypercube Sumcheck claim is the same as an eval check. Okay, so there's a lot of questions that remain to be answered. This is a preview of what's going to happen. Questions that remain is like, how do these reductions work? Like, what's happening in a round? What is R prime I? What is SI? What makes a protocol even valid? So let's talk about the mathematical desirable properties that we have. One is called completeness. This basically is that an interactive protocol is complete when an honest prover can convince a verifier of any true fact. So if I'm starting with a true fact, and I'm a prover that's honest and I'm following what I'm supposed to do, then the verifier will accept with 100% probability. That is completeness. It's complete. Any true statement can be proven. Soundness, right? The argument is sound basically means that a dishonest prover will fail to convince a verifier of any false fact. So if I'm a dishonest, malicious prover, I can try and find some false fact, and I can try and convince the verifier that it's true and give it like a fake proof. But no matter what I do, because the protocol has been designed well and it's a sound protocol, the verifier will reject with extremely high probability. So completeness, honest prover always succeeds. Soundness, dishonest prover will succeed with extremely small probability. So a small technical note, which I'll just quickly skip over. There's like many forms of completeness and soundness. We use something called perfect completeness and adaptive computational soundness. The only thing that I'll sort of stress here is that, like, as a computer scientist, you should very much care about the distinction between two types of randomized algorithms. Randomized algorithm number one is for 99% of inputs, this works all the time. Randomized algorithm number two is for all inputs, this works 99% of the time. The second is more desirable. right? Especially in like cryptography and snarks. You want it to be the case that like no matter what input you choose, you do not have a good chance of cheating. It should not be the case that like most inputs will be okay, but there are some that might. There shouldn't be special inputs. You never want your randomness in these randomized algorithms to be over the inputs because that gives you no guarantee. Like you should, as like a computer scientist, you usually don't make assumptions about the distributions of your inputs with an asterisk. Sometimes you can, sometimes you can't. But generally, you want your randomness to be over like the coins of the algorithm, and you have a guarantee no matter what input you choose. You don't want your randomness to be like it works for most inputs. Okay, because like one of the cheating vectors that a dishonest prover can do is it can try and find a false claim to prove. So, anyways, yeah, that's a little bit of a rant and a tangent, but perfect completeness, adaptive computational soundness. If you'd like to read those on your own time, you can, but it's basically what I said, that a cheating prover has a very small chance of convincing you, even if they get to try and pick the fact that they're trying to convince you of, or the fake fact. So, given my earlier claim that it's good to think about Sumcheck as something that reduces a k-dimensional thing to a k-1 dimensional thing, I argue that we can just dive into what a round of Sumcheck looks like, just this reduction from k variables to k-1 variables, and that should be sufficient for us to understand all of Sumcheck, because all of Sumcheck is just applying that round n times, applying like around n times, right? To keep knocking down one variable until we get from n variables to 0 variables. So let's just focus on what a round of Sumcheck looks like. So in round k, our goal is to reduce a Sumcheck claim about a polynomial on n minus k variables to a Sumcheck claim about a polynomial on n minus k minus 1 variables. So the claim before round k looks something like this. We're summing over n minus k length bit strings. And the claim after round k and before round k plus 1 is something like this. We're summing over n minus k minus 1 length bit strings. They're half as many as n minus k length bit strings. And the things that we want to hold true are completeness and soundness. So completeness means that if round k claim was true, then if you follow the protocol honestly as a prover, then the round k plus 1 claim will also be true. Soundness means that if the round k claim was false, then no matter what you do as a dishonest prover trying to pull a fast one on me with this false claim, the round k plus 1 claim that you'll get out will also be false. So those are the desirable properties that we want in order for Sumcheck to be a good protocol, in order for this like round of Sumcheck to be good. So let's now high level talk about what a round of Sumcheck is. A round of Sumcheck works like this. Step 1, the prover sends a univariate round polynomial, one variable, round polynomial, to the verifier, claimed to equal this. So, small technical note, what does it mean? This already is like a very complicated expression, but it is a polynomial. When I say like the prover sends the round polynomial, it doesn't just send like the expression like as a string for how to evaluate this. No, no, no. Basically what it does is it does the work of like figuring out what this simplified into monomial coefficients would be, right? Like if you really evaluated this crazy looking sum, you would eventually get something that looks like a0 plus a1x plus a2x squared, blah, blah, blah. So the prover is doing the work of figuring out like what those monomial coefficients a0, a1, a2 are, right? Another technical note, this is what the prover is supposed to send, right? Some monomial coefficients that equal this value, like such that these two polynomials are equal. Recall that a dishonest prover might not send that, but for now, let's like talk about the protocol for an honest prover. So it sends a univariate round polynomial, Rkx, to the verifier. Rkx is guaranteed to have degree at most d, where d is the total degree of the composition polynomial g. Why this is, we will detail in just a second. But for now, take my word that Rkx is a univariate polynomial of degree at most d, and therefore it can be represented by d plus 1 monomial coefficients. Step 2. If the prover is honest about Rkx and the round k claim is true, then it must be true that Rk0 plus Rk1 is equal to the claim Sk. The verifier checks if this is true. If not, it rejects and it stops the protocol right there. Step 3. The verifier samples a random challenge R prime K from some cryptographically large extension field L, and it sends this challenge to the prover. Step 4. The prover and the verifier both compute the round polynomial that was sent at the challenge point and sets this to be the new claimed value for the next round, Sk plus 1. And so the round k plus 1 claim polynomial is fk plus 1x is equal to fk, specialize the first variable to this challenge, and then have x. So as desired, fk plus 1 is a new polynomial on one fewer variable than fk had. Okay, so here are some steps. We don't know yet why they're useful, but these are the steps. This process requires V to evaluate this round polynomial at some point R prime K that it's sampled. The complicated compute intensive step, and that we should talk about how it works algorithmically, is step 1, where the prover takes this very complicated looking expression and it computes the monomial coefficients. Like it simplifies it into its monomial coefficients. We'll talk about how it does that, but for now, just imagine that the prover has some algorithm, it does it, and it sends the round polynomial to the verifier. Okay. So before we talk about this complicated algorithmic step in step 1, we are going to talk about why this round protocol is mathematically desirable. And here is like the cool part from the math side of why this works. We want, if the round k claim is true, the round k plus 1 claim is true, completeness. And if the round k claim is false, then with high probability, round k plus 1 claim is false, soundness. Completeness. Suppose round k claim is true, and you follow the protocol, so the round polynomial is what it should be. Then Rk0 plus Rk1 is equal to this expression plus this expression, which if you squint hard enough, you'll see that this is literally the same thing as this, right? This is like the first half of the hypercube evals, and this is like the second half, or maybe the odds and evens, depending on your layout. Together, these two sums is the sum over the entire n minus k dimensional hypercube. And since the claim was true, that's equal to sk. So if you send the right round polynomial as a prover, then the verifier check will pass if the round k claim was true. Now let's sample any random value. The new claim is sk plus 1, which is the round polynomial evaluated at that challenge point, which is equal to this, right? Just like by definition, this is what the round polynomial is supposed to equal. Change this r prime k into an x. And this is equal to this because like this is how we defined this. Like fk plus 1x is equal to fk r prime k x. So these are all just kind of like true definitionally. So this is the easy. Completeness proofs are usually like very trivial. It's like, okay, you followed the thing, it works. So if the round k claim was true and we sent the right round polynomial, then the round k plus 1 on fk plus 1 and sk plus 1 is also going to be true with 100% probability. Okay, soundness. Any questions there so far? I want to pause. Making sense? Okay, awesome. Soundness. Suppose the round k claim is false. Then the dishonest prover can choose like any d plus 1 monomial coefficients and say, hey, this is the round polynomial. Case 1, you send the real round polynomial, i.e. like the polynomial you sent actually is equivalent to this polynomial here, this complicated expression. Then RK0 plus RK1 is equal to like summing over the entire hypercube, like the result of summing over the entire hypercube. And that's just not equal to the claim because like if it, we're saying the round K claim was false. So these two things are just not equal. So the verifier check will fail. And here's the important thing, right? That means the dishonest prover must send a round polynomial that is different from this real round polynomial, let's call it. So it must lie about the monomial coefficient simplification of this round polynomial here. So in this case, we have that this claimed round polynomial that's been sent is not equal to what the real round polynomial should have been. By polynomial identity testing, if we pick a random challenge point with high probability, these evaluations will not be the same. And this is defined to be the new sum, the new claimed sum. And this here is defined to be the new multivariate polynomial. So if these guys are not equal, that literally means that the round k plus 1 claim on fk plus 1 and sk plus 1 is false. So that's the punchline, right? The dishonest prover has to send a dishonest round polynomial, otherwise the verifier check will fail. And once you send the dishonest round polynomial, you basically only propagate a false claim on k variables to a false claim on k minus 1 variables. So like we've now detailed how a round of Sumcheck works. If the original claim is true, we do n rounds of Sumcheck, knocking out one variable every time. After every round, you have a simpler, one fewer variable, Sumcheck claim that is both true and whose truth value is a good measure for the previous claim's truth value. Each round, the verifier receives a degree d univariate round polynomial, samples a random challenge from some large field L, and evaluates the round polynomial at this challenge point, creating the next round's claim. So this is the only work that the verifier needs to do every round, which is very minimal. At the end, you get an eval check claim. If the original claim is false, the original Sumcheck claim, you do n rounds of Sumcheck, and at some round, you need to hope that you go from a false claim on round k to a true claim on round k plus 1. If you're a dishonest prover and you're trying to convince me, that's what you hope. That somehow like false claim, false claim, false claim, suddenly you get like a true claim. Otherwise, you failed as a malicious prover. So by polynomial identity testing, the like polynomial identity testing must fail at some round because at some round you're sending like the wrong round polynomial, but somehow like those evaluations turn out to be the same. And that happens with probability like at most d over the size of L, the number of elements in this large field. So the probability you cheat successfully in round 0 or cheat successfully in round 1, blah, 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 is at most the probability you cheat in round 0 plus the probability that you cheat in round 1 plus dot, 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 dot. This is like a very common thing in math called a union bound. So you get this expression, you get this expression, and this here is your soundness error, which basically is like an upper bound on the cheating probability of a dishonest prover. Like successfully cheated a verifier with a false fact. You can do that with probability at most of this, no matter what false fact you originally started with. Now, looking at this like soundness error, you can see why we want L to be a large field. We want this denominator to be super large to keep the soundness error really small. And typically we have like a target for how small we want the soundness error. We say like 100 bits of security means that we want like this value to be like 1 over 2 to the 100. Cool. So yeah, that's like the math behind Sumcheck protocol, a round of Sumcheck, and what makes it like a mathematically desirable protocol is completeness and soundness. Any questions on like what's going on here? I'll put it here. Okay, cool. If you guys are comfortable with that, that's already like huge. This is like literally what Sumcheck is. And understanding this is already huge in understanding like what Sumcheck does. Every round you're sending a round polynomial to the verifier, expressed how is like the monomial coefficients. And it's basically like simplifying this like beast of a right-hand side polynomial. And yeah, every round the verifier does a check. The verifier samples a random challenge, and then the prover and verifier both compute the round polynomial evaluated at that random challenge to get the new claimed sum. That's it. That's like literally all of Sumcheck. Now, the rest of what we'll talk about is kind of talking about the algorithm for how the prover actually figures out what the monomial coefficients of this round polynomial is. Because that's where a lot of the like algorithmic complexity lies in. So let's talk about computing the round polynomial. And now we only care about honest provers. The whole discussion of dishonest provers and trying to cheat, that was for the last section. We talked about why if you try to do that, you're not going to be very successful. Um, Now, the rest of what we care about algorithmically is like we have an honest prover trying to prove true claims. How efficiently is the prover able to do this? So, recall in the kth round of Sumcheck, the prover must send a round polynomial to the verifier, represented in monomial coefficients. So, the kth round polynomial is supposed to be the simplification into monomial coefficients of this beast of a right-hand side expression. And fk is really if you like unroll what is happening right here. If you unroll this all the way back to f0, which is defined to be f, then you can see that fk is nothing other than f just evaluated, uh, specialized with its first k variables being the k like round verifier challenges that have been sent. So rk of x is equal to this as polynomials. Now, this, as you can see, is like, a bunch of terms, and every single term has the only indeterminate is in the xkth spot. So that means that the degree of this round polynomial is equal to the individual degree of xk in f. And the individual degree of something in f is less than or equal to the maximum individual degree of f, which is less than or equal to the total degree of g, which we've defined to be d. And so this is exactly why I said, I promise you that this round polynomial, even though this is like some really complicated expression here, when simplified to its monomial coefficients, this should have degree at most d. Okay, so ideally we can represent this round polynomial, rk, with d plus 1 coefficients. So a0, a1 up to ad. This is called the coordinate vector with respect to the monomial basis 1x x squared. But how are we going to actually do this, right? Like this is like some ungodly complicated expression. You can imagine that if you had like a pen and paper and you had this sum term and you wanted to figure out like what a0, a1, ad are, you would like expand it out. You'd do like a bunch of like you literally do all these like evaluations, and then you do some like simplification and grouping by terms and maybe some foiling and factoring. God knows, it's disgusting. But that's not how we do it. That's not how we figure out what a0, a1, ad is algorithmically. That would be horrible. Instead, we do something smarter, which is we realize that a degree d univariate polynomial can be uniquely determined by d+1 evaluations, right? A line can be determined by 2 evaluations. A quadratic can be can be uniquely determined by 3 distinct evaluations, etc. Degree d univariate polynomial uniquely determined by d+1 evaluations. So what we can do instead is we can figure out what Rk of x is at x equal to d+1 different points, 0 to d inclusive. And once we get that, we can somehow turn that into the monomial coefficients. Recall that like these things here are nothing other than Lagrange basis coefficients, which means like evaluations at specific points. Lagrange basis coefficients we can turn into monomial coefficients by using something called a change of basis matrix, a change of basis linear transformation. Now, don't worry too much about how that works. Happy to talk about like what that matrix looks like, but the most important thing is just to know that it exists and that it's standard. And there is like a very simple matrix that will take you from Lagrange basis coefficients to monomial coefficients and vice versa, the inverse of that matrix. Takes you the other way. Cool. So that's going to be our strategy as a prover to compute the monomial coefficients of Rk of x is we'll first compute the Lagrange basis coefficients of Rk of x, which means that we're just going to evaluate it at d+1 different points. Awesome. So take one of our algorithm. Recall that f of x is a multilinear composite of this form. We initialize an array of of size d+1. That's going to be our evaluations of Rk of I. Ith thing is going to be our evaluation of Rk of I. Like it's going to be accumulated as we go through every single term in the sum. And we'll do this loop for every single hypercube point, for every single capital X in 0 to D. What we're going to do is we're going to evaluate all the underlying multilinears at the point H R prime X V. Maybe I'll like write that explicitly. So like the jth element is HJ R prime. Oh, sorry. R prime X V. Oh, it's already written here. Oops. So we'll get all these multilinear evaluations. And then we'll evaluate the composition polynomial on the multilinear evaluations. And that's like evaluating f at the point R prime xv. And we will accumulate, we'll sum up, and we'll sum up over the entire hypercube. And by the time we're finished with this loop, evals is the coordinate vector representation of Rk of x with respect to the univariate Lagrange basis over the domain 0 dot 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 d. In English, the ith value of evals is now Rk of I. We've computed it. Cool. Now to get the monomial coefficients, we just take the change of basis matrix that turns Lagrange basis coefficients into monomial coefficients, and we multiply it by the evals coordinate vector, and we get the monomial basis coordinate vector, and we just return that. Cool. Yeah, so that's the algorithm. What I'll say is like this works, but there's a lot that's underspecified here. Like everything in star, how we're actually like summing up evals really requires a lot more attention to detail and like explaining how we do things. Like how are we actually evaluating this multilinear HJ? There's smart ways to do it, there are dumb ways to do it. Okay, so one thing I'll say is that like, okay, so for V and blah, 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 then we do everything here in star. Everything here in star is called in our code base in Rust, process vertex in the Sumcheck evaluator trait in our open source Rust code. So let's talk about how we can be smart about evaluating all the multilinears over all the x's and all the v's. This symbol here, in case you're not familiar with it, stands for all or for each. Okay. How do we evaluate a multilinear? Assume that we have the Lagrange basis representation of a multilinear. In English, assume that we have the 2 to the n hypercube evaluations of a multilinear. Okay, this is pretty much always how we represent a multilinear. Okay, we want to evaluate it at a point R. The first method that you're probably familiar with is we evaluate the Lagrange basis polynomials at R. That's the same thing as this tensor expansion. And then we dot product the Lagrange basis polynomial evaluations at R with the Lagrange basis coefficients, right? So generally, how do you evaluate like a polynomial? You take its basis polynomials, you evaluate it at the point, and then you dot product it with the coefficients. So that's exactly what's going on here, just like special case to the Lagrange basis. And that gives you A of R. So this is what the tensor expansion looks like. And this is also exactly equal to the Lagrange basis polynomials being evaluated at R. You get something that looks like this. I'll zoom in. And then these evaluations are actually Lagrange basis coefficients. Take this dot product, and you get the evaluation of A at R. So this is the method that's kind of like normal, that you're more familiar with. The second method is you specialize each variable through linear interpolations, and you do this folding procedure. So for each I in 0 to n minus 1, we specialize xi in A to Ri. We get a new polynomial, which has one fewer variable. And this new polynomial's coordinate vector length has halved as compared to this polynomial's coordinate vector length, right? Because this is now on like n minus I minus 1 variables, and this was on n minus I variables, right? We've halved in terms of the length of the coordinate vector. After doing this n times, you have taken a coordinate vector of length 2 to the n, and you've turned it into a coordinate vector of length 2 to the 0 for the 0 variate polynomial A R0, but like specialized at all of its variables at R. And this like one value that you have left is literally your answer of what AR is. For example, you start with A as like a 2 variable multilinear, and then you fold it once and you get this. Oh, give me a second. I should spend the effort to write this out properly. This is like, oh, sorry. Give me 1 second. A1 of 0 is equal to A of R0, 0. A1 of 1 is equal to A of R0 of 1. So now you get like the coordinate vector of a different polynomial, which has one fewer variable, that's specifically A1. And then you get this. And like, how am I combining these two elements to get this element? It's through a linear extrapolation, rather. So look, AR00 is equal to this, right? Like pretend like this guy was constant. Then I'm just like extrapolating over this first variable, right? I have the evaluation of 0, I have the evaluation of 1, and I want to figure out what happens when I replace this first variable with R0. That's a linear extrapolation over a certain axis. And why can I do that? Because A is multilinear, so it is indeed linear over that axis. Okay, so I'm basically doing like this folding. And what it really is I'm like taking this, multiplying it by that, taking this, multiplying it by that, plussing these guys, the results, and combining. And I'm doing this chunk by chunk. And then I keep doing that, and I get this result. So these are sort of two ways to evaluate a multilinear, right? I can fold it n times until like 2 to the n values have become one value. Or I can just like create the entire tensor, like, and then do a dot product with the 2 to the n values. 2 to the n vector dot product with another 2 to the n vector. Two ways to do it. Specialize one variable at a time, or just like kind of one shot it. Now, notice we are evaluating multilinears in round K at this point, at these points, right? So these are fixed and these guys vary. X varies all these d plus 1 points, and v varies over the n minus k minus 1 dimensional hypercube. So one thing to notice is that like, hey, these guys are fixed, and these guys like really are not taking large field values. In fact, if we're smart, we can evaluate like from xk onwards at only 0 or 1 hypercube points. How that can be done is like, okay, we'll see the magic and how that's possible in a sec. But if we're smart, we can like, make sure that we only evaluate multilinears from xk to xn minus 1 taking on values that are 0 or 1. You might be like, okay, x could be 0 to d, but that's something we can actually fix. So that's one observation. We can be smart. Second observation is that multilinears in round k plus 1 are evaluated over like these types of points, which looks very similar to these types of points. So that sort of suggests that like pattern suggests that we should reuse some computation from the previous round. These are two observations we'll exploit. Exploiting observation 1. Fix some multilinear, j star. So we're looking at one multilinear. To evaluate h of j star at, okay, you fix the first k variables, and then vary x over d plus 1 points, and vary v over the n minus k minus 1 dimensional hypercube. Here's the first thing we can do. We can create a partial tensor, right, of size 2 to the k, which corresponds to these first k challenges. And then for each I, or like basically for each vertex in the n minus k minus 1 dimensional hypercube, we like dot product this partial tensor with the chunk, like the 2 to the ith chunk of size 2 to the k, and that gives us this evaluation. Now, I'm going to skip over method 1 because it's a little complicated. I'll come back to it. Let's talk about method 2 first. For each I in 0 to k minus 1, right, we can specialize, like basically we can fold k times, right? And once we folded k times, right, for the first k variables, we get a new folded multilinear, capital H j star, which is on n minus k variables, which looks like this. And then for each v star in 0, 1 to the n minus k minus 1, we can read this value because like everything in the input is a like 0 or 1, so we can just read it. It's in our coordinate vector somewhere. We can read this value. And then for each x and 2 to d, we can like literally just extrapolate along the xk to x. Maybe to make it even clearer, I'll change x to like z so that you can see that it's like a value. Cool. So like this is our improved method, right? Like rather than, every single time we want to evaluate this multilinear anywhere, we just like always fold and then always fold all the way, always fold all the way. What we do is like we fold like the first k times, we get this new multilinear and its new coordinate vector representation, and then we kind of like be smart. We like for each hypercube point, we evaluate it at 0, x equals 0, x equals 1, and then to get x equal 2 to d, we're like doing an extrapolation, a linear extrapolation using 0 and 1. And what we've accomplished is like, other than the first k variables, which are fixed to be these challenge points anyways, we never have to evaluate this multilinear anywhere off the hypercube. So that's kind of cool. Method 1 is exactly the same thing. And let me kind of explain how method 1 works with an example. I know this looks daunting, but I promise it'll make sense. We have A. It's a multilinear. Oh, shit. It's a multilinear on 4 variables, right? suppose k is equal to 2. So we have some partial tensor that looks like this. We want to evaluate like a r prime 0, r prime 1, 0 v, and a r prime 0, r prime 1, 1 v for every single v over the n minus k minus 1 dimensional hypercube. Okay, basically we're trying to like get this value and this value, right? But using method 1 and using like this weird partial tensor thing without doing these foldings. So we're keeping like a in its original form. We're not actually folding a. We create this partial tensor. Now, if we like look at a specific v, so we'll iterate over all the v's. Let's talk about v is equal to 0 first. This corresponds to like I equals 0. So if we look at like the 2i plus 0 with chunk, gives us chunk 0, right? We can talk about chunk 0 dot producted with our partial tensor and say that that's exactly equal to a r prime 0, r prime 1, 0, 0. We can talk about chunk 1 dot product with our partial tensor is equal to a r prime 1, 0, right? So that gives us like exactly what we wanted. We got the 0 value, we got the 1 value for fixed v. How the hell did that work? Well, you can think about defining a polynomial like a0 x0 x1, which is equal to this, a x0 x1, with these two values fixed. Similarly, you can think about defining something like this, with these two values fixed to 1 and 0. And when you do that, how would you evaluate a0 at r prime? Well, you would evaluate its Lagrange basis polynomials at r prime 0, r prime 1, which gives you this, and you would dot product it with a0's coordinate vector, right? It's a0's Lagrange basis coefficients, which is literally this chunk. So we're doing the normal process of evaluating a multilinear polynomial on fewer variables, on k variables, using the partial tensor and this chunk. And so the key insight here, and you can review this like a slide at your own leisure, and it'll make more sense when you just stare at it, is that the Lagrange basis coefficients of a multilinear on n variables can be interpreted as a size 2 to the n minus k array of chunks, where each chunk is Lagrange basis coefficients of multilinears on k variables, where each smaller variable specializes n minus k variables to be a different n minus k dimensional hypercube point. That's a lot, but I promise if you read that a couple times, it's very specific and it explains exactly what's going on here. So this partial tensor dot producting with a chunk, giving us some like actual evaluation that we care about, stems from this idea of just like defining a polynomial on fewer variables where you sort of specialize some of the later variables of the original polynomial. It's a cool math idea. I promise that if you look at the slide at your own leisure, it'll make sense. But I'm going to skip over this in the interest of time. The main idea, again, is that by doing these smart methods, and it's easier to see in method 2 how this is happening, we are making sure that we never really evaluate our multilinear at places that are outside the hypercube, right? The first k challenge points are fixed. But then other than that, we're making sure that all the other variables only get looked at zeros or ones. So it makes sense how we do that from xk plus 1 to xn minus 1, because that's like v and it takes on only hypercube values too. The cool trick is that we can even do it for xk, right? The thing that varies from 0 to d. And the way we do that is we fix the hypercube point. The r prime before it is already fixed. So now we have like a univariate polynomial that's like only varying over xk. We take the 0 evaluation, we take the 1 evaluation, and we extrapolate along the xk axis to get 2, 3, 4, 5, all the way up to d for xk. By doing these cool tricks, we basically made sure that like we can evaluate these multilinears in a very impressive way algorithmically. So that was the hardest part, and we're almost done. We'll exploit observation 2 now. we're using method 1, we've already computed this partial tensor. So for round k plus 1, we need to compute the partial tensor of one more variable. Might as well reuse what we've already done and just take it one step rather than going k plus 1 steps from scratch. Similarly, if we're using method 2, we've already like folded the multilinear k times. So might as well in round k plus 1 just fold one more time rather than starting from the original representation and folding it k plus 1 times, right? Just like reuse the useful data structure that you had, whether it's a folded multilinear or whether it's like a partial tensor. Again, just reiterating, partial tensors is basically the same thing as like Lagrange basis polynomials evaluated at some point, R prime. To see that, I would look at the previous lecture. Take 2 of the algorithm. Okay, we have evals. It's a length d plus 1 vector for each hypercube point over n minus k minus 1, right? So now, at this point, like once we've inside this for loop, v is fixed, r prime is fixed. The only thing that's not fixed now is x, right? The thing that varies from 0 to d. So we initialize arrays of length c for 0 multilin evals, 1 multilin evals, and z multilin evals, where the jth element is going to be equal to this: r prime 0v, r prime 1v, r prime zv. Recall r prime is fixed, like because that was already fixed from previous Sumcheck rounds. V is fixed because we're processing a specific vertex right now, and we're inside this loop. So this like x variable, xk variable, is the only thing that's changing. For each multilinear, right, we populate evaluating that multilinear at the desirable point, depending on what the array is supposed to do. Then we will process eval 0 is plus equals to g at the 0 multilin evals. That's exactly equal to f r prime 0v. So it's like one of the terms that we need for calculating rk of 0, one of the hypercube terms that we need. Similarly, we do this. Now, for 0 and 2 to d, and for each multilinear, right, we linearly extrapolate hj r prime xk v at xk is equal to z. And then we get eval z plus equals g of z multilin evals, which is equal to this. That's just one of the terms in trying to calculate rk, the round polynomial, at x equals z. Once we finish this procedure, evals is the coordinate vector representation of the round polynomial with respect to the Lagrange basis. So it's just the evals of the round polynomial at 0 to d. We can turn it into monomial coefficients just by applying the change of basis matrix as before. And we get monomial coefficients out. That is how the prover is able to compute the monomial coefficients of the round polynomial. Interesting thing is how one evaluates these multilinears, right? Is it through using method 1, where you're doing like this dot product with a partial tensor, or is it using method 2, using like folding and just like reading it from your like array, reading the hypercube element that you care about right now from the array, the hypercube evaluation. Either way, observation 2 tells us we should reuse data structures from previous rounds. Technical note: method 1 is what we refer to as pre-switchover, using this partial tensor. Method 2 is what we refer to as post-switchover, folding the multilinears. Round 0 is sort of a trivial case, like because if you want to evaluate the multilinear, it's somewhere on the hypercube, it's like you just read it. It's there. Okay, that concludes that section. One thing I'll make a note of is how many times are we evaluating g, the composition polynomial. That's usually the thing that we look at for performance. One thing that we look at in the performance of computing the round polynomial is like, how smart we are about like doing these multilinear things. But the composition polynomial can be super complicated and have like a lot of field multiplications required. So we look at how many composition polynomial multiplications we have. 2. Here it is every single hypercube point. So there's 2 to the n minus k minus 1 of them, multiplied by the number of places we're evaluating the round polynomial at, so that's d plus 1. questions on this section? Okay. I recognize that this is hard stuff and that this might require like going back and taking a look at the notes. If you feel like you're in that bucket, for anyone listening, don't feel discouraged. This is the sort of stuff that requires repetition. The last section is very simple. We're just gonna some notes on performance. Method 1, right? This partial tensor thing is space efficient in earlier rounds because basically like 2 to the 24 F2 elements is smaller than 2 to the 23 128-bit elements, right? That basically just stems from this idea that if I specialize one of the variables x0, then now all of the evaluations have bumped up from like a 1-bit to a 128-bit. Yeah, so like keeping around the original representation of the multilinear and keeping the small partial tensor can be more space efficient than folding the multilinear. Unintuitively, folding the multilinear, even though it gives you half as many like hypercube evaluations, can blow up space because each hypercube evaluation now can go from like 1 bit to 128 bits to represent the value. Second important performance note, the degree of G matters, denoted as D, it matters because it tells you how many times that you need to evaluate the composition polynomial in a round. Remember, it's 2 to the n minus k minus 1 multiplied by d plus 1. The degree of G matters. Similarly, the number of like field elements required to evaluate the composition polynomial G also matters. So that's why we care about like corners and these other smart ways to evaluate the composition polynomial. There are many performance optimizations. I'm just going to list them. I'm not going to explain them. You don't actually need to evaluate x at x equals 0, ever. For the first round of Zerocheck, you also don't need to evaluate at x equals 1. If you have a Sumcheck instance that has a specific form, right, you would expect that the round polynomials to prove this Sumcheck instance would have degree d plus 1. Like if f has degree d, f bar, since this is multilinear, bumps up the degree of f bar by 1. So f bar would have max individual degree d plus 1. So you'd expect the round polynomials in proving Sumcheck about f bar to also have degree d plus 1. But you can be smart, modify Sumcheck a little bit, and make the round polynomials you send also degree d. The smaller the round polynomial degree, the more efficient, because the fewer like G composition polynomial evaluations you have to do. So that's nice. There's all these tricks. I'm going to be talking about these tricks and their implications in great depth in the next lecture. They're also important, but for now, I wanted to just present the completely unoptimized version of Sumcheck because it's easier as an introduction. But yeah, that's Sumcheck in a nutshell. I know this was a lot to put into one lecture, but hopefully, like with the recording and the notes and being able to ask me questions, we'll be able to make sense of this together. So cool. Yeah, that's it. Any questions from you guys before I end the recording? And then you can also ask questions after I end the recording. But
all good for me. Thank you, Kabir.
Cool. Yeah, I'm gonna end the recording here then. Let's see. How do I do that? Stop recording.